All right, gang, Mass 6620, more on simple linear regression, multiple regression. And my grandmother used to say when something was important, she would say, well, that's where the rubber meets the road. I don't really know what that means, but I guess we can say that with this video. This is going to get into some uh, very comprehensive look at regression. The game plan here is to start out with simple linear regression, and I can tell you that there are 5 parts, and I've written it out there. I'm not going to read it to you, but we're going to start out just looking at the data, looking at examining the distribution of anxiety and exam. That's going to be the purpose of this first analysis. We're going to get into some case-wise stuff, diagnostics, residuals, and different things. So the first thing I want to do is what? Uh, Probably need a better game plan than what I have, right? I guess the first thing I'd want to do is take a look at my predictor, which we're going to predict again, exam score from anxiety. So I would probably want to look at the mean for anxiety because I'd want to definitely report that. And I'd want to look at the standard deviation for anxiety. But more importantly, I'd probably want to take a look at the distributions. So it might be a good thing to do, take a look at a box plot of anxiety, see if there are any outliers. And you can see there are a lot of outliers. So I am proceeding cautiously with regression models. We have 7, I believe. Yeah, I haven't worked this problem out, so I'm doing this for the first time. We have 7 outliers, and I have a feeling these 7 outliers are going to cause a lot of chaos in our model. And it actually works out well if I demonstrate this technique in a situation where there are issues, because if everything was just perfect, then you would learn how to do carry out regression techniques in that situation. But if you run into problems, you may not know where to turn. So we're going to know where to turn here because we have some issues there. Next thing I probably want to do is look at a box plot of my dependent variable exam. Looks relatively symmetric. Don't have a lot of concerns there. I would probably want to run a Shapiro test on my predictor anxiety to see if we do have normality. And you can see that we just violate the heck out of normality for our predictor anxieties. So again, I am expecting that we're going to have some major issues with this model. So first thing I think I'd want to do, and I'm just going to refer to this as model. So I'm going to run it, predict exam from anxiety with data equal data, summary model. All right, a few remarks here. When I look at this, a couple things I want to point out. First of all, in the simple linear regression case, we can see that the t-squared, which is the coefficient test statistic, will be the same as the model F statistic. And in general, the t-squared distribution squared is the F distribution. So what we could do here is we can take negative 4.938 and square that, and we'll see that we get the F statistic, which is a model diagnostic. More about that in just a second. And we see that we could construct the p-value for the F distribution on 24.38, degrees of freedom 1, 101. And my bad, got sloppy there. Remember the p value for the F distribution is in the upper tail. So we get the same thing as we do for the predictor. Now, this is only going to happen when we have a simple linear regression case. I think we've talked about this in a previous video. Next thing I'd want to do is I'd want to report the multiple R squared. And in this case, I would say the 19.45% of the variance in exam score, got fat fingers today, is explained by the regression on anxiety. Next thing I would look through that. Now, you can see that there's a multiple R squared and there's an adjusted R squared. Anytime we give multiple predictors, more than one predictor, we'll use the adjusted R squared. But anytime we have one predictor, we'll use the multiple R squared. The next thing that I would want to do is I'd want to interpret the coefficient estimate for anxiety. So what we would say here is we would say as anxiety increases 1 unit, the predicted exam score decreases because our coefficient is negative 0.67 units. Next thing I would want to probably look at is now remember this negative 0.67 is the estimate, so we may want to look at the confidence interval. And the confidence interval for this estimate would be negative 0.93 to negative 0.40. So it does not contain 0, which tells us we have statistical significance. And we get the confidence interval for the intercept as well. It's just not nearly as interesting as is the predictor anxiety. Another thing, you may want to comment on the model diagnostic. And you would report that as, of course, F1 101 equal the test statistic of 24.38, p less than 0.001. And I feel like there's something I'm forgetting here. Let me explain to you what the model diagnostic is actually telling you. If we create the null model, where we take predict exam from 1, and then compare the two models, so the null model with the model we created predicting exam from anxiety, see that we get some familiar numbers, right? 24.384, which is what we get for the F statistic, and okay, well, it's just in the residual degrees of freedom. So, and we get the p-value, which of course is the same as we get up there. So that's what the F value is actually reporting to us. So we have a statistically significant model, and we have a statistically significant predictor in anxiety. Now we're going to get into the nuts and bolts to see if our model is really worth using to predict exam score from anxiety score. So the next thing I'd want to do is I would want to check for outliers and influential cases. So I think what I would do here is I'm just going to create things that I'm going to talk about. So first thing I'd want to take a look at are the standardized residuals. And I'm having a hard time typing today. I feel like I'm making typos everywhere. Next thing I want to do is Cook's distance. Next thing I'll talk about will be our DF betas. Next thing will be DF fits. If you don't know what all this stuff is, don't worry, I'm going to teach it to you. What else do we want to look at? Let's look at our leverages. And let's look at the covariance ratio. Hopefully all that was okay, no errors. Again, sometimes I get fat fingers and I create typos. Now, what I would like to do is create a new data set here and create a new data frame with anxiety, which is my X predictor, exam, and then I want these values. Attach new data, and let's just look at the first few cases. So you can see that we get the values that we want to investigate to see if we have any cases, influential cases, or X outliers. So the first thing I want to look at, I guess the best place to begin would be the very first one, is standardized residuals. Now, remember, a residual is just the difference between the observed y and the predicted y. A standardized residual is the residual, again, observed minus predicted, but it's divided out by the standard error of the residuals, which we saw above. Typically, standardized residuals, we have red flags if we have anything above 2 or below -2. And the way I would identify those is I would just do my new data, let's call those standardized residuals, right? Greater than 2, or new data, standardized residuals less than -2. And what I'll get, if either one of these are a true statement, in other words, if we have any standardized residual above 2 or below -2, I'll get a true, and you can see that I actually have that, right? And I have one right here. So that would be the 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101. So it's going to be the 101st case. So what I may want to do is I may want to take new data 1 and isolate that case and see what's going on with it. So I want to choose the 101th case, and I want all variables. So new data 1. So I can see the 101st case for the standardized residual. I have -2.12. So I would need to put a little bit of thought into potentially deleting the 101st case. Now, would I delete it? I don't know yet. If it shows up in any of the others, I would seriously consider. So for right now, 101 is on my agenda for being deleted. Now, the reason I'm kind of wishy-washy on this is 2.12, -2.12 isn't a long way from 2, so it's not going to have a lot of influence, not to be confused with this other stuff. So I probably, if this had been above 3, then yeah, definitely. But, I don't know. Right now, it's still on my radar. The next thing I probably want to take a look at are the Cook's distance. Is that what we have next? Yeah. And Cook's distance is just a scaled change in our fitted values. And it helps us identify X outliers. So what we do with Cook's is okay, if I come across, for example, for the second case, what does that Cooks tell me? It tells me that if the second case was deleted, uh, this value shows a scaled change in the fitted values. So again, for high Cook's values, and I'll set the threshold here in just a second, it could identify issues with X value outliers. The standard for Cooks is if we have anything greater than 1. So what I can do is go back up and get my command from here. Instead of standardized residuals, I can look at Cooks. Anything greater than 1 is going to give me some concern. So I eyeball through there, and I can see that I do not have any cases. So I have no concern with Cook's values. The next thing we get are x-intercept and anxiety. These two actually go together to create what are called DF betas. And a DF beta is another case-wise diagnostic which gives me the coefficients of the new model if that case was deleted. Now, right now, if we go back to our model, we'll see that the coefficients are negative 0.67 and 106.07. Well, if case number 3 was deleted, our new x-intercept would change 0.41. Our new anxiety would decrease 0.0029. So we want to identify those cases that have a large influence, quote unquote, on the x-intercept and the anxiety when deleted. Now, it turns out for DF betas, the, um, there's I don't know, conflicting information out there on that. And I really never know where to turn. Some resources say that a general fit, we could use 2 as a threshold. Others tell me that we need to use a size adjusted fit, which is 2 divided by the square root of n. If we take 2 divided by the square root of n, I don't remember what the sample size here is. I believe it's 103. Okay, so if we took 2 divided by the square root of 103, we can see we get a threshold of about 0.20. So if we go back up and look at the same kind of command, yeah, this will work. And look at x-intercept, so greater than 2. We see we get all falses. And if we run that for our anxiety 1, you'll see that we get all falses. Now, using the other threshold, the 0.20, I believe things will be drastically different. And there you see we get a lot of red flags. I don't even know what, 1, 2, 3, a lot of them actually. So that would require quite a bit of work and diving in and looking at these values and seeing the ones that are relatively high and seeing if the cases show up in other diagnostics that would justify removing them. If we go up and point to for the estimate for the coefficient, we get all falses. Now, for me, if the intercept moves around a lot, I'm not really as concerned. I would have much more concern on the predictor, anxiety. And it looks like to me as I eyeball those, all are false. So I would proceed with no concern on the DF betas.